Welcome to Maths with EJD. In this video, I'll start talking about mathematical induction. And in this first one, our focus will be on introduction to mathematical induction. I'm sure you're excited to come along in this journey. Okay, in the outline, we'll be looking at the principle of mathematical induction, proof techniques in mathematical induction, strong induction and weak induction, advanced inductive proofs, applications of mathematical induction, real-world applications of mathematical induction, and some conclusion. And that will set the stage for the other videos to come in this series. All right. So let's talk about the principle of mathematical induction. Mathematical induction is a powerful proof technique used to prove statements about natural numbers. Of course, in case you don't know, natural numbers are the normal counting numbers, 1, 2, 3, 4, 5, 6, and so on and so forth. So those are natural numbers, all right? So mathematical induction is a powerful proof technique used to prove statements about natural numbers. So we have to pay attention that it's for natural numbers. Of course, there are two steps in this process. You have the basis step, which here you prove that the statement for the base case, usually n equals 1 or n equals 0. Okay, so first case, n equals 1. And then there's the inductive step where you assume that the statement holds for some arbitrary k and prove that it holds for k plus 1. Now, I mean, in my own practice, what I do is I actually break this down into 4 steps. All right. So in my case, I have them broken down into 4 steps. So whatever statement you're making, maybe you're saying that, oh, all positive numbers can be summed up in a particular way, if you're saying that, or for instance, the very popular one I've been talking about is the fact that 1 plus 2 plus 3 plus 4 is equal to n, plus all that up to any value n is equal to n times n plus 1 divided by 2. That is, if you want to add from 1 to any number, you take that number, multiply it by the next number, and divide by 2. So if you want to take care of this statement now, so for me, I break down these two the basis and deductive steps into 3 stages. So the first for me is where I prove the statement for n equals 1. Then of course that's actually enough. But I mean, to really convince you that you're doing the right thing, I also like to prove the statement for n equals 2. And for 3, I assume that it is true for n equals k, since there's really no way to prove that. So you just assume, just like you have it, assume the statement holds for some n equals k. And number 4, finally, which is the inductive step now, then you now prove it for n equals k plus 1. Okay, so I go over that again. So you have the basis step. So in my case, right, I told you that I like the basis step to be in 2 ways. I like it to be n equals 1 and n equals 2. So this is like my own basis step now. Then this is the inductive step where the first part is an assumption, and then the n equals k plus 1 part is the actual proof. So that's how I like to do my own. And of course, you're going to see so many questions. After this video, we'll start taking different kinds of questions that can come up in this regard. Okay, so that goes. So let's talk about proof techniques in mathematical induction. So there's actually direct proof, and this is straightforward application of the principle. That's direct proof. Then there's also the idea of strong induction, and this assumes that the statement holds for all integers up to k. That is, so you do the basis step, like in my own basis step now, you do 1, 2, and then it goes all the way. Then you assume that it is true for k, and then that will lead you to proving it for n equals k plus 1, like that. Okay, and of course, there's the weak induction, right? Traditional induction, assuming the statement holds only for k. So for that traditional induction, you assume the statement holds only for k, that you don't care about these other ones, but you just assume for only k. And then you just go ahead and prove for n equals k plus 1. But I mean, for the purpose of this series, I'll be focusing on strong induction, where we prove it for the base case, for my in my own case, I choose n equals 1 and n equals 2, and then I assume for k, and then I prove for n equals k plus 1. So strong induction is what I will adopt all through this course. Okay, so let's talk about strong induction and weak induction, right? Strong induction is proving that P of k plus 1, the statement evaluated at k plus 1. Yeah, so you prove the statement at k plus 1 by assuming that P of I, by assuming P of I for all I less than or equal to k. So it means you're proving it just like what I've said previously. You're proving it from for n equals 1, n equals 2, of course. And once you're able to establish it for n equals 1, n equals 2, most likely it is true for 3, 4, 5, 6, 7, and then up to k, you know. And then from there, you can now prove that it is true for k plus 1. But for weak induction, you just prove straight that p equals k plus 1 by only assuming that p equals k. By only assuming p of k straight. So here, for weak induction, you just jump straight to k. But for strong induction, you start from 1 up to k before you prove for k equals for k plus 1. And that is, again, I'm adopting the strong induction technique. So both methods are logically equivalent. I mean, they are basically the same thing. So you can see just the only difference is that for weak induction, you jump straight to k and prove k plus 1. But for weak induction, you jump straight to k, you assume for k straight and prove for k plus 1. But for strong induction, right, you check the base case n equals 1. And then for me, I like to add n equals 2. Sometimes I even go as far as n equals 3. So once I'm able to establish those, then I assume for k and prove for k plus 1. So that's basically the difference. So weak induction, jump straight to k and prove k plus 1. Strong induction, start from the base cases 1 to as many as you want to choose, and then assume for k and prove for k plus 1. So both methods are logically equivalent, like we've said already. Then strong induction often simplifies proofs or handles more complex cases. And that is exactly why I've chosen to go with strong induction. So let's talk about advanced inductive proofs. So for complex cases, right, sometimes proving statements with induction requires creative thinking. That's extremely important. Creative thinking and even some additional techniques like nested induction. So nested induction is like, so nesting is like, you are doing something, and along the line, you now have something come up inside it, and then like that until you narrow down the issue, right? So nested induction, here you're using induction within an inductive proof. So you're proving something, and it gets to a point where you need to now prove another thing to prove the main thing you want to prove, right? So that's like how it goes. And then you have the induction on multiple variables. So this is proving statements dependent on more than one variable, right? So that's possible. I mean, we'll hardly come across some of these things in this series. Induction with divisibility too. So utilizing divisibility properties in proofs. So you see, sometimes you want to prove that a particular expression is divisible by 9. So we are going to see how to tackle some of these issues. So, and it's important. There are some rules for divisibility generally. For instance, how do you know that, of course, all numbers are divisible by 1? That's for sure. Then how do you know numbers that are divisible by 2? Any number that ends with 0 or any even number is divisible by 2. We know that. How do you know a number is divisible by 3? If you can add all the digits together, and it adds up to a multiple of 3, then you know it is divisible by 3. How do you know a multiple of 4? You know, all those rules exist. A multiple of 4, right? It's you know, okay, there are all those rules which I don't remember. For 5, for instance, any number that ends in 5 or 0 is divisible by 5, and so on and so forth. All those rules exist. Okay, so you have applications of mathematical induction, right? What is the importance of mathematical induction? I mean, for people like me who have a background in applied mathematics, we have a little bit of aversion for for proofs, where you have to think abstract and prove that something is something. The mathematical induction is just that technical, is that maybe like it's your introduction to being able to prove stuff. And these things are necessary, right? Because they have real world applications. So, I once had to work with somebody who is into cybersecurity, like a postdoc, a doctoral person in cybersecurity, right? And she has to give some mathematical basis for what she's doing. All right. So you can see that mathematical induction is actually applicable in real life situations. So mathematical induction finds application in various fields like number theory, then, of course, combinatorics, computer science, analysis of algorithms, set theory, and graph theory. So all these areas, you have mathematical induction being pretty much useful. Then even in talking about sequences and series, convergence, and things like that. Okay, so that's applications. All right. So, I mean, we are narrowing down now specific stuff, real world applications of mathematical induction now. So, for instance, you want to prove properties of sequences and series in physics and engineering. That's one real application. Then you can also talk about analyzing algorithms for correctness and efficiency in computer science. That's like at some very advanced level in computer science. Then how about verifying properties or recursive functions in programming? That's also useful. Then what about establishing theorems about networks and communication protocols in telecommunications? Now, some of these things, for people even who operate in these areas, it may look strange to you, but at the very highest levels, at the very advanced levels, these things are pretty much useful. Okay, so, in conclusion, right, mathematical induction is a fundamental proof technique with wide-ranging applications across various disciplines, showcasing the power of mathematical reasoning. So it's all about being able to reason mathematically, and bring things to life and show that things can be proven in a particular way. Okay? So, yeah, and this is a very funny practice question because I've not actually done anything. So probably this is the first question I'll take in my next video. So practice questions. Prove by induction that the sum of the first n positive integers is s equals n plus 1 all over 2. So that's the same thing I've been saying about add from 1 to any number. So that's the first thing I'm going to prove in my next video. Then again, number 2, use strong induction to prove that every positive integer greater than 1 can be expressed as a product of prime numbers. So we can also lay our hands on that probably in the next video. So come along. If you have not subscribed at this point, you'll be missing a lot if you don't do that. So subscribe, hit the notification bell so you can get alerted when a video comes. Then like, comment. I mean, your comments can include something like maybe you need clarity on something, you need us to solve a problem, you have a question for us, you want me to treat a topic, that can be like your comment. And then share it too, because I know there are many people that this will be very useful for. Thank you so much for coming along this far. Thanks for listening. I appreciate your time. Keep coming back so we can solve our maths problems together because maths can actually be fun. So see you in the next video.